All right, here's our second and last video for section 10.5 on volume. Remember, we already talked about the volume of a rectangular solid, we talked about the volume of a pyramid, and then we even talked about the volume of a cylinder. Now let's talk about the volume of cones and spheres. So if I have a cone, it's kind of like a pyramid. The only difference between a cone and a pyramid is that on a cone, the base is an actual circle instead of a square or a rectangle or a triangle. But we're actually going to still use that same formula for a pyramid. Remember the formula for finding volume of a pyramid was 1/3 times that big B, the area of the base, times the height of the pyramid? Well, if a cone is just a circular pyramid, well then the area of its base is really just pi r squared. So you could say 1/3 big B times h, or for the cone specifically, you can say that the volume is 1/3 pi r squared h. Remember, it's height, not slant height. And then you're going to do pi r squared for the radius. All right, let's do an example here of a cone, just a basic example. If I give you this cone off to the side and I ask you to find the volume, we know that the volume of a cone is 1/3 pi r squared h. So I'm going to plug in my radius of 7 meters. I'm going to plug in my height of 10 meters. I'm going to multiply all of that out, and I got 490 over 3 pi cubic meters if I was doing it in terms of pi. If I were dividing that or multiplying it out, I would end up getting 513.13 cubic meters. Make sure that you show me your setup. Make sure that you can do it in terms of pi, and make sure you can give me a volume multiplied out if they ask to the correct decimal place. All right, that was cones. The last volume we're going to talk about is a sphere, so a ball. We can find the volume, how much space any ball takes up, by doing 4/3 pi r cubed this time. That's the radius times another radius, right? And so 4/3 pi r cubed would be a volume of a sphere. Let's do example number 6. This talks about ice cream. Ooh, yeah. All right, but your little bratty kids are in the back with their ice cream. All right, and this ice cream cone is 5 inches deep and has a radius of 1 inch. So you have ice cream cones in the back of your brand new car. Your ice cream cone is 5 inches deep with a 1 inch radius. And you've got a perfectly spherical scoop of ice cream that has a radius of 1 inch. If the ice cream melts into the cone, will it overflow into the back seat of your new car? Well, let's see. Can we figure out how much ice cream there is, the volume, how much space that ice cream takes up, the volume of that sphere? And then can we figure out how much space the cone's going to take up, the volume of the cone? And if the cone has a bigger volume than the ice cream, then it shouldn't melt, right? But if the ice cream has a bigger volume, then it's going to overflow into the backseat of your car. So we got to do a couple different things here. We've got to figure out the cone, we've got to figure out the volume of the sphere, and then we got to compare them. So go back, find the formulas for the volume of a cone, find the formula for volume of a sphere. You should probably pause the video, work out both of these things, and then compare them. See if you get the same answers that I do. All right, for my cone, I have a formula for volume as 1/3 pi r squared h. I know that the radius of this cone was 1 inch, and I know that the height of the cone was 5 inches. So when I worked that out, I got 5/3 pi inches cubed. I could multiply that out and put it into a decimal form if I want to, but I'm going to stop there for now. I'm going to look at the sphere, the ice cream, and see how much volume the ice cream is going to take up so I can see if it's going to spill in my car. The formula for volume of a sphere is 4/3 pi r cubed. I know that the radius of this ice cream is 1 inch. And so I can say that the volume of the ice cream is 4/3 pi inches cubed. And so it's actually a very nice fraction comparing both of these. I have a 5/3 pi and a 4/3 pi. And so is it going to overflow? Oh, phew, it is not. Hopefully, if your kids are nice and neat and keep that ice cream in that cone, because the cone has a bigger volume than the ice cream, it should all just nicely go into the cone and not overflow. Okay, kind of using volume a little bit different of a way. All right, the last little thing we're going to talk about in this section is surface area. So we've been talking about volume, which is kind of the space something takes up, but surface area is kind of the outer surface of a of an object, a three-dimensional object. So if you think about maybe wrapping a present, right? How much wrapping paper would you need to go around all of the outside surfaces is a little bit different than how much volume the present takes up, right? All right. And so when we're talking about surface area, we're really talking about the stuff on the outside. Area here, area here, area here. And so our units are actually just square units now. They're not cubic units anymore like we did when we did volume. Okay? Here are a couple of different formulas for surface area depending on what kind of figure you have. You have cubes here, we have a rectangular solid here, and we have a cylinder here. Okay? Let's do our last example in this section and find the surface area of this rectangular solid. And so what we want to do is figure out how much area is on the outside of this three-dimensional figure. And so I need to figure out what is the area of the left side, what is the area of the right side. Well, both of those sides are rectangles, aren't they? And so we know that we can find the area by doing base times height, or length times width. I know that the base here is 5 yards, and it looks like the height here is 3, isn't it? And so I can do 3 times 5 and say 15. And aren't there two of those exact same shapes, the left side and the right side? So can I really say that there are two 5x3s? And that'll give me the left and the right side. Now, I also have to do, let's see here, let's do the top and the bottom. So if I'm looking at this top and the bottom, they're the same shape, rectangles. I know that the length here is 8. I know that the width here is 5, right? And I know that there's two of them, a bottom and a top. So I can do 2 of the 8x5s. That was the top, the bottom, the left, the right. Don't I also though have a, can I call it a front and a back? Isn't that right here? Also a rectangle that has a length of 8 and a height of 3 this time. There's a front and a back. There's two of them. So I should be able to say 2 times 8x3s, right? 2 8x3s. I'm going to multiply all these little numbers together, making sure you follow the correct order of operation. And so we have the left and the right side being 30 square yards, the, top and bottom being 80 square yards, and then the front and back being 48 square yards. If I have all of that wrapping paper added together, I know that I need a total of 158 square yards of surface area of wrapping paper. Okay? All right, make sure you know how to use all the different formulas for volume and even surface area now, that you can apply it to do all different types of problems, kind of like the swimming pool problem and the ice cream cone problem. Practice all of that good stuff in this unit. I'll do another video probably covering a few problems from the extra practice worksheet, but you should be working on that as well as the review before you go ahead and take your last test of the semester. Let me know if you guys need anything.